from Croatia University of Technology, like I already said, and I got introduced to the NARS project 1 year ago, and since then I'm working with Pi on this non-axiomatic reasoning system. And this talk now is about assumptions of decision-making models in AGI. At first, let's compare it with traditional assumptions. In traditional decision-making models, like in reinforcement learning, like in Markov decision processes, in game theory, and so on, the following assumptions are made. There is an assumption on task, namely that the best evaluated action from a given list, predefined list, is chosen, and this is done for each state. And the second assumption is on belief, namely that consequent states are given by a probability distribution for each action. This is, for example, we have a state S1 and a state S2, and we have an action which with a certain probability will change the state S1 to the state S2. On desire, it's the case that these decision-making models assume that the system's desires are given by a value function defined on states. And on budget, it's the case that they assume that there are always enough existing resources to use the defined selection algorithm. In AGI, the situation is a bit different. Like we see, these assumptions don't hold. Namely, on task, it's a big part of the problem is which candidates you want to consider for your decision making. So this is different than in the traditional models where I have a fixed set of actions and I will evaluate all the consequences for all the actions. This is different here. We only consider certain actions. On belief, the assumption we previously saw does also not hold, because neither the preconditions nor the consequences of an action are fully specified. For example, because under insufficient knowledge, there will always be preconditions we don't know about, and there will always be consequences of our actions we don't know about. So the system can only describe parts of the situations and parts of the state of affairs it has to deal with. So, and on desire, there's the problem that how much a situation is desired cannot directly be measured. There are different aspects of situations, aspects and parts of a situation which the AGI system desires, and part of the situation which it does not desire. So its desire of a situation is very context dependent and depends on what the AGI system wants to achieve. On budget, it's the case that the system cannot afford the resources to always consider all the possibilities, and we strongly think that this is the case for AGI. Now I will present a decision-making model called NARS, where all the assumptions we saw are not made. NARS, also called non-axiomatic reasoning system, is an AGI system which is designed to work and to adapt under insufficient knowledge and resources, to work in real time with variable time pressure, and to be always open to new experience. Or the different cognitive mechanisms like reasoning, learning, decision making, and so on are all achieved using a single technique, namely through reasoning. Also, it is the case like I already mentioned, that the decision-making process does not depend on the previous assumptions. Truth value. This is how the system judges the truth of certain beliefs. It's in NARS different than in traditional logic. There's not just true and false, but there's a entire space between true and false, and this is also because the system has to be able to deal with positive as well as negative evidence which votes for a certain statement, whether it's true or whether it's false. And the judgment whether a specific hypothesis is true or false can only be judged according to parts of past experience. There will never be enough resource to remember everything which happened in the past in detail over the entire lifetime of the system. Also, there won't be enough resource to consider all the combinations of what happened in the past and to consider all the possible interpretations what may have been the state of affairs in the past. So, truth value in NARS has two main parts. This is the positive and the negative evidence. I prefer this as the basic definition because it's very natural that specific evidence can vote for a specific hypothesis and negative evidence can vote against it. And based on this evidence, we define the W as the total evidence, which is the sum of positive and negative evidence. And already with this, we can define the so-called frequency value F, which is defined like shown above. The frequency value says basically a sort like a success rate. For example, if you observe a new kind of animal on a island and you see it has a red head, then you had total evidence 1 and positive evidence 1, so frequency would also be 1, and the confidence according to the total evidence just is some sort of evidence counter which the system uses to judge the stability of a certain belief, how stable, how supported it is by past experience of the system. In NARS, there are 3 basic types of tasks. The first one are the judgment tasks, which are absorbed into beliefs. This is basically the knowledge the system has about its environment. Then there are questions which the system can answer and will, for example, ask itself. And there are goals the system has to achieve. And these are the 3 basic tasks. And it's the case that in most reasoning, the derived tasks will be of the same type like the parent task. So judgment or knowledge will derive knowledge, questions will derive questions, goals will derive sub-goals. But there are some cases where this is not the case. For example, it can be that a judgment of high importance to the system, but of low confidence may raise questions for the system. Also, it might be that a question may raise the motivation to find more about it. Also, it might be that a goal, that goals cause certain beliefs, and this can, for example, also generate questions. But this is already far into the detail. Basically, judgments are used to derive judgments, questions to derive questions, which are answered by judgments, and goals the system has to achieve, and which can be, where the system can see how much a goal has been achieved by looking at the truth value of the judgment. And for goals, NARS takes the truth as the desire as truth approach, which means, like you see below, if we have a gore G, then the truth value of from G follows D is the desired value of that gore. And this D is just a virtual statement for a desired situation. This is just some technical detail. And this way, all the reasoning or the truth value calculations which are done for the judgment can also be used for the gores. That's the point of it, to keep it simple. Operations in NARS. Operations are basically like other events for the system, except that the system can make them true whenever it wants to do so. And these operations, which are provided to the system, can either change the environment. For example, in a sensory motor interface, there might be an operation for turning a motor off or on. And it might also be about internal states for introspective decision making, where the system, for example, decides to consider thinking about a certain concept, and this then happens by increasing the related priority of this concept. And the point of this is that the system can actively control its attention in its decision-making process. And the most important information about operations are its pre and post conditions. So a typical belief is like below: precondition, operation, and consequence. And this is probably the most important form of beliefs in the system. And decision making in NARS means basically the decision for the system whether to pursue a gore. Such a gore operation is just a special case which the system can make true itself, but basically decision making is for the system, in a narrow sense, deciding whether to pursue a gore. What's different to traditional models, different to there, where we have an atomic list of actions. This might not be atomic actions. This can be on different levels of description. What might be atomic actions on low level might be entire strategy on high level. So this mechanism also works for strategies. And the decision whether to pursue a gore is based on the desired value of the statement. If it's desired, for example, to execute an operation, then it will do so. If it's desired to achieve something, the system will try indirectly to achieve it. But in a broad sense, of course, all activities in the system contribute to the decision the system will make. Now we'll get back to the assumptions, and we will see how NARS does not assume the assumptions of the traditional models at first. The task on decision making is not to select one from a given list of actions, but decide whether to pursue a gore, like we already saw. And in most situations, the applicable actions are not explicitly listed, but need to be found or composed. There might still be cases you can still give the system or let it know about action it can use, but it's not generally assumed that there has to be such a list. And an important aspect of the decision making, how it's done, is by derivation of subgores via backward inference. And all times when this happens, the system has to revise this new gore with the already existing desires of this. This way, the system will always try to resolve conflicts in its desires. For example, it might be out of curiosity interesting to do something risky, but on the other hand, if it's too risky, one won't do it. So there has to be, the system has to try to be consistent. Or maybe better example, if you're short in time and you desire to go to the cinema or to go swimming, there might not be enough time to do both. So these goals can also be conflicting with each other or competing with each other. Then on the assumption of beliefs, it's the following, that the consequences and preconditions are expressed as statements by the system, so they are not states like in the traditional decision-making models which describe the entire situation, because in an AGI system, the exact internal state, the entire situation, may not repeat in its entire lifetime. There are different aspects of different situations which may repeat, but it's unlikely that the exact same situation will be the case again. This is why we take the statement approach, where we don't need an atomic state which describes the entire situation. But still, if the system has enough resource, it can, in simple cases where it's really possible to combine all the details about the situation into a single statement, it's still possible, but it cannot be generally assumed that this is possible. Then, truth value in NARS is not probability, it is based on partial past experience rather than the objective world. Then, the system's beliefs can be inconsistent. This, for example, dependent on how about what you think, you may reach a different conclusion about a certain thing, or dependent on what sources of information you consider. Then the assumption on desire. The desire values summarizes its relation with the other considered goals. This is what I meant with the revision, with the already existing desires. And those goals come and go in real time, and this way the desire values cannot be obtained from a function that maps state to utility or reward directly. There might be aspects about situation the system desires and aspects it doesn't desire. Interestingly, the behaviors of an AGI will not be determined by a single supercore, but by many given or derived cores that compete with each other. And there's even a more interesting aspect about this. It may even be that the subcores of derived subcores may become independent. So they don't vanish if the supercore, if the core was derived from is fulfilled, because then the system would have to remember always when it derives a core or the core, the entire derivation chain of how it derived that core. And it's also not necessarily, like by argued, this core alienation is an important aspect of autonomous systems. Then the assumption on which optimal decisions made with sufficient resource and optimal decisions made with insufficient resource are different problems that demand different solutions. This means if you take the insufficient knowledge assumption out of the system, you end up with or if you take it out of the AGI problem, you end up with a different problem. In our point of view, an AGI has to make the best of the resources it has. If it is not able to make the best of the resources it has available, that's, in our opinion, an important aspect for an AGI system to be able to do this. NARS works in real time, which means to handle each problem instance according to its demand on response time and case by case, rather than depending on a decision-making algorithm with a fixed resource cost. This also means that the system is able to adapt to variable time pressure, dependent on how much time it has. In the certain situations, it may come to other conclusions and about other decisions. In short time, this is a very important aspect. that the system won't sit for an hour, or if it doesn't have that much time just to evaluate all possible things which could happen. This is whether the system has enough time or not is highly context dependent, whether it will be successful or not. If successful, the related concepts will survive, and this way the system can adapt to variable time pressure. The conclusion of this talk can be summarized as follows: that the fundamental assumptions of the traditional decision-making models cannot be satisfied in the context of AGI for the reasons we talked about, and that NARS is a normative model for decision-making that does not make any of these assumptions, and we also stress that it's important for an AGI system to assume the work with insufficient knowledge and resources and to make the best of the resources that it has. With the resources it has. And this is nearly everything. There are certain examples which we tried with this model. This is not the fun part. Just this, for example, is here it's the following. It's a rover. This is the rover, and it tries, the core of the system is to collect rectangles, and it only receives the reward if it really is able to catch it. So in this case, the reward is delayed, and the system has to interpret its field of view in order to achieve what it desires. And this is also a nice example because it shows the strength of the temporal reasoning the system has in it. And yes. Another example is Pong. This is also just for fun, also with delayed reward, because before the ball does not reach the left end of the simulation, it doesn't know if it reached the ball or not. And when it reached the ball, it gets reward. Its desired states get entered into the system, and if not, then not. Then also interesting, this is one of the things where I think there's a lot of potential in AGI systems, because AGI systems, at least like NARS is, can make of observed symmetries and apply all its structural reasoning to the situations it observes. For example, so if we have board games, there are a lot of rules which don't change over the entire game. All of this is a very unnatural situation for an AGI system like NARS. It's at the same time a fascinating one because the system can make use of its deduction abilities, and it can try to identify the game rules and all this stuff. Or there might be better general game playing systems which already assume the stationary or the staticness of the environment. It's still interesting that an AGI system like NARS can use its reasoning to hopefully perform better than a blind reinforcement learner in such a domain. And this, the nearly last example, is the test chamber. This one we designed for different cognitive experiments. Here you can just drag switches and doors into the simulation and lights and keys in order to open a door. And here you can try different things. For example, you can force the system to take the key and go into the room and to activate the switch in order to turn the light on. And then you can let it go out. And for example, you can enter the goal for the system that it should make the light on again. this may be very easy for some planning narrow AIs, but for NARS this is already challenging because it has to judge all the observed correlations in its experience. So it may be that it forgets some part of what it did before, and this creates very interesting behaviors, because whenever it, for example, is not sure about something, it will try something again, and in order to find out more about how to reach the desired states. And here it's also with we also try to experiment with things like partial observability, where the system, for example, does not know the, for example, here we have two switches which activate this light, but the system does not know that this AND thing here is the reason why it needs to switch on both switches. It can only, by own experience, if it goes into and activates this one and goes here and activates this one, experience that by doing this, that this light goes on. So, for example, it's already an abstraction for the system if it went this way, that it also would work the other way, to activate this switch at first and this one as second switch. Already interesting that this is not trivial if you gain all your knowledge from the experience and not pre-given. And this one is just for fun. Here it gets rewarded if it goes to the right side, and it of course tries to learn that it needs to jump over, that it needs to jump up and then press the right button in order to get over obstacles and such things. But those examples I showed now, except of the previous one, were mainly reinforcement learning tasks, and I also chose them to show that this decision-making model really works, that this is not just theory, but something which can be tried by everyone. We have an open NARS implementation, which everyone can download at our open NARS page, and everyone can try these examples on his own. Thank you for your attention.
We have very short time for some questions.
In your presentation, you mentioned that you didn't think it was possible for an AGI behavior to be determined by a supergoal. I absolutely accept that given NARS's architecture, it's not possible for NARS's to be, but I don't accept that an AGI with a different design cannot be determined by a single supergoal. What is your evidence for making such a strong claim?
The evidence is that, for example, if you let me think one moment. The evidence is that there are often different goals which we as human beings observe in our life. For example, if I'm hungry, I'm at a foreign city, for example, and I get hungry, I will behave according to this context-dependent goal that I need to get food. Well, in general, it could be claimed that there is a sub-goal which describes the overall happiness of the system. This is true, but it's mainly this context-dependent goals which motivate the system to do certain things in the specific situations. So a general supergoal is still available for the system to be to be as happy as possible, but the system cannot directly reason about the supercore, but about the bad cores, which are context dependent. Does this answer the question?
I think we'll have to have this discussion over a few beers later.
Okay.
Okay, let's thank Patrick again.
I have a question for Tony. How do his experiences compare to your experiences implementing NARS? I mean, you're another guy who's actually implemented and played with NARS yourself, right?
Yeah, and we've actually been working together quite closely over the last
yeah, I see.
In what sense?
Well, I guess my big question about NARS has always been that I like probability theory. Right. And Pei believes probability theory is not an acceptable approach to AGI. I mean, in that sense, I'm much more mainstream, right? Like, I think probability theory works. I mean, to apply it in its full accuracy and splendor is not tractable, but then you seek approximations to it that are calculable given the resources at hand. This approach, throw out probability theory and you adopt totally different axioms for managing uncertainty. And I'm wondering if any of the experimentation you guys have done with NARS provides direct support for the NARS uncertainty formulas in contrast to probability theory.
I don't think they're exclusive. I think they're both valid approaches. I've not had anything that said now is not a good way of doing it, but then probability approaches, PLN is another way. That's not a problem with any system. It's the control aspects that are the problem with all systems. It's attention, it's how you allocate resources. That's where the challenges come, and there isn't a theory for that yet. I think there's loads of solutions for logic. There just are no solutions to control theory.
Another long discussion, but go.
Can I add something?
Yeah, please do.
I think that probability is not wrong. It's just that probability needs the system to know a lot, namely to know the probability space it is working in order to derive new conclusions which are correct according to probability theory. I think it can be repaired to some extent, but it demands a lot of resource. For example, if new information comes in, at least maybe you have solved the problem somehow, but for the entire probability distribution needs to be adapted to that new information. While in NARS, the new information won't need to update the entire memory, but
we don't need to do that in PLN either. I mean, the solution to that is just, or a solution to that is just not to maintain a consistent overall probability distribution. It's just in the context of each inference, you cobble together a consistent distribution for the things you need to consider in that particular inference. And you just don't try to construct an overall consistent distribution. So that particular problem doesn't have to exist.
But we are concerned about if one is not able to achieve a global consistency in the memory of the system, if I still derive new conclusions, how can I revise them? There are no rules in probability theory which would tell you how to go from one probability space to the other. This is the main concern, but I think
we published a load of papers on how to do that belief revision using higher order probabilities. I mean, there's math solutions to that too. But I kind of agree with your statement in that in the 2004 through 2007 period, Matt Clay and I and a number of other colleagues, we spent a lot of time deriving very nice mathematical formulas for probabilistic logic inference, and partly because we're mathematicians and like doing that work, it's fun. And then you do that and you realize, well, okay, we have these very accurate probability heuristic calculation formulas, and indeed, controlling inference and dealing with combinatorial explosion in inference is a much harder problem, so we're not even using most of the fancy math we derived back then yet. So I think that's true. That, I mean, ultimately I personally think probability will form a better foundation than the NARS logic. However, I agree the control problem is harder than the math of uncertainty manipulation. So. Let's let Abram say something. He's
So I just wanted to ask how much computation resources are required to run these examples, how long, like how many times does that have to try in order to do something interesting? So how feasible are these to run in kind of real time or?
It's the case that the system, since it works under the assumption of insufficient resource, it follows the more resource the system has to use, the more resource the system can use, the better it is expected that it will perform. But there is technically
but like, does it take seconds, minutes, hours for you in practice running it?
you can stress the system as much as you want, and if you stress it more, it will try. It's forced to come up with faster solutions and with faster decisions. And depending on this, if you stress it too much, it won't be able to do something good. But if it has enough time or enough computation, fast enough processor to do the same computation in the same time, then it's better. Or these examples run on a weak hardware also. Even if it's 10 years old, this shouldn't be a problem.
Okay, I think we're ready for the next talk.
Oh, it is,
Yeah, but it's time.
okay.
Next, we have Ben Goertzel discussing the deep reasons for the deep pathologies in deep learning, in deep networks.